Now that we've looked in depth at the structure of methane, understanding that it's tetrahedral, we're going to briefly take a look at what's called the methyl group. Now, a methyl group is simply CH3. And of course, the carbon has to have something attached to it. And so there are a series of compounds called methyl compounds in which the CH3 is attached to some X, right? All right, so uh, one thing to understand is that after a hydrogen is replaced by another atom or group of atoms, the pure tetrahedral symmetry of methane is actually lost. We'll see how that plays out a little bit down the road, but when you replace one of the hydrogens with another atom, X, these are called methyl compounds. Now, what is X? Well, X is simply a substituent, right? A substituent, a group, right? It could be a functional group, and that's what it typically is. So a functional group is really a substituent coming off of a generic alkyl group, and in this sense, a methyl group. So as we've seen, there are various X groups that are possible. So let's look at some examples here. Well, when X is hydrogen, obviously CH3H is CH4, and so this is simply methane. But when we change it to, let's say, an OH, remember ROH is an alcohol. So when you have CH3OH, this is called methanol. Notice we drop the E and we replace it with an OL. And this is going to, we're going to see this general trend emerge throughout the chapter, right? I can replace the hydrogen with an NH2 group, and this becomes methylamine, right? Again, amines are kind of strange, I guess you could say. Not necessarily strange, but the nitrogen can have different R groups coming off of it. In this case, it has two hydrogens, and so this is called a primary amine, but it can have another R group coming off of it, and then it would be a secondary amine, and it can even have two more R groups for a total of 3 R groups, which would make it what's called a tertiary amine, right? We can also exchange the hydrogen for a bromine or a chlorine or an iodine or fluorine, any of the halogens, and we get methyl halides, or in this particular case it's called a methyl bromide, but in general any halogen is called a methyl halide. We can also replace it with cyanide, so it becomes methyl cyanide. Now, methyl cyanide also has a common name called acetonitrile. Acetonitrile is a solvent that organic chemists often use. And, you know, if you named it methyl cyanide, a lot of people would go, oh my gosh, it's very, you know, dangerous and whatnot. And in fact, methyl cyanide or acetonitrile is not that dangerous at all because of the strong carbon-carbon bond that exists in the structure. Last example is if I exchange the hydrogen for an SH, and this becomes methane thiol. So thiols are named a little bit different than other compounds. You actually keep the base alkane name and then simply add thiol to it. And we'll get into naming a little bit later. Now, in terms of the structure of these methyl substituents or methyl compounds, we note, and here I have methanol, right, CH3OH, and if I take a look at the structure, it's very similar. You know, it has a tetrahedral-like geometry, but the bond angle between that hydrogen-carbon-oxygen bond is actually greater than 109.5. It's around 111 degrees. And so the carbon itself is not quite sp3, but it sure is close. It's like an sp 2.8. But for all general purposes, we can still treat this as an sp3 hybridized carbon, right? One thing that I want you to focus on is how you draw tetrahedrons, right? Um, some students have a very difficult time representing a three-dimensional structure of a tetrahedron. And I'm going to lay out some groundwork that I want you to practice on so that we're all kind of in the same ballpark. There's a couple of ways that you can draw tetrahedrons, and I'm going to go over both of them right now. So in one rendition, the first step that you're going to do is you're simply going to draw two lines in the plane with a bond angle of about 110 degrees, right? Representing that tetrahedral geometry. So the next thing that you need to do is recognizing that those two bonds, if those are in the plane of the board, then I have one bond coming out of the plane of the board and one going behind the plane of the board. The way that I draw that is that I take those two lines and I draw a wedge at an angle kind of going down, right? And then I also draw a dash at an angle going down. This gives me that three-dimensional quality of a tetrahedron, and I can simply add, any groups that I want to, A and B and C and D, to this particular structure. Now, another way that I can think about drawing a tetrahedron is simply changing the angle of the two lines. So let's say I had an angle that looks like this. Well, in my second step, where are the dashes? Where's the dash and where's the wedge going to go? Some students will draw it pointing down and all sorts of things. Remember, the dash and the wedge are going to be in the same direction and opposite the angle that you draw of the two bonds that are in the plane of the board. So in this case, that angle is down, so I'm going to draw the dash and the wedge up, right? And I can think about, now this is a really cool lesson that we can think about, is where A, B, C, and D are actually going to go relative to the drawing that I drew in the first place, the structure above, right? So if I say that A is in the lower right-hand corner and B is in the lower left-hand corner, what have I done? Well, relative to the structure above, I have simply rotated that molecule about, 60 degrees or so. Well, what does that mean? That means that C is still coming out at me and D is going behind me. So these two structures are actually equivalent with one another. Now, another way I could have drawn it is with the point down, the angle up, and so now the wedge and dash are pointing down. And again, if I said A is here and B is here, what have I done? Now I've basically rotated the upper structure 60 degrees in the opposite direction. C is still coming out at me and D is going behind me. So think about, that's a nice little practice to try to visualize the three-dimensionality of structures, because we're going to be spending a lot of time thinking about how to draw structures and represent them in 3 dimensions. And it becomes very important for organic chemists to do this.